All right. Thank you. That means everybody's here today. And I can go ahead. Now, do you have the slides now?
Roger.
Okay. Thank you. Yeah, I shared the screen. I forgot to change the screen. Anyhow, okay. So try again. Describe the types and properties of different kinds of cables and connectors, and we already did that. Twisted pair, coax, fiber optic, serial. Fiber optic is probably the preferred media because of its invulnerability to a lot of the interferences, but it's also pretty expensive to make. The fiber itself is not so expensive, but the connectors are, and the materials to put it together are. Where we talk about twisted pair, we have some RJ45 connectors and some scissors and crimpers, and we're ready to go with that. Understand the use of wiring standards when selecting cable for different applications. One of the things that you probably will need to know is the order for the twisted pair, the orange and white orange, green and white blue for the B standard, and then you swap 1 and 3, 2 and 6, and we'll talk about that whenever you create a crossover or use the A standard. Understand the use of interface and media converters. What that means is we're going to come in with fiber perhaps, or come in with twisted pair and leave with fiber, and that can be done. There are devices that do that, and switches do that in many cases also. Identify the appropriate tools for network hardware installation testing so that we can test our twisted pair to be sure that it actually has been created correctly. This is the copper cable where each pair of wires is twisted reduces to reduce crosstalk, and that's what these things are. The crosstalk is the interference from one wire to the other. Let me see if I can make one of my bad drawings here. If we had two pieces of wire running parallel and we put a signal on one, that signal actually would be induced into the other cable, and if we had the same sort of signal here, they would build on each other. What the twists do is to move the cables slightly out of phase, and this right here would be noise, and that's what we're worried about: crosstalk, interference, and noise. If they're not twisted, they're going to produce interference with each other. If we're twisted, we make a little bit of change, and the twists are all at different numbers of twists on each of the wires. When we look at this thing here, the pairs themselves, we have 4 pair. The pairs themselves are twisted, and inside the cable itself, there also are twists when we do those. Unshielded twisted pair is what we predominantly have, and that's what this one is. There's no shielding around it. The newer cables have foil on them. We'll look at that here in just a second. But if we're going to upgrade the cable for a higher throughput, then we got to upgrade the patch panels, the wall plates, the connectors, and the infrastructure. Remember yesterday we said that the infrastructure should last about 10 years. We're in many cases with twisted pair getting to that 10-year point, to where we're going to go from the 100 base. When we went from 10 base to 100 base, not a whole lot of changes had to be made. We had to go from 10 base switches and hubs to 100 base, the hardware. We'll go from 100 base to 1,000 base to gigabit. We have to change all the components. We've got to go in and change the connecting components also when you do those things. And all of these things have a CAT standard. It's not just for the wire. The connectors and the interconnects are also have CAT standards or category standards when we have those things. Shielded twisted pair in its origin was for token ring, and it actually had a shield around it. The new stuff in the little picture here has foil, and if you see the FUTP or FTP, SC screened twisted pair, all of these are going to have foil around them, and this helps with noise reduction. And noise is the enemy of all of these things when we do that. When we have the wires here, they're, let me see, they said they're 22 to 24 AWG. AWG is American wire gauge, and wire is measured in gauge. And the higher the number, the smaller the wire. So if you get to like 110 volts, you have what 12 gauge wire that we might use in a house. So the modern foil screened is the FUTP, FTP, or SCTP. So the modern screened and shielded cable is S/FTP. And if you look at these over here, it really depends on how much foil we have. The F/UTP, the foil goes around all of the pair. The UFTP, the foil is around the individual pairs. And the F/FTP, the foil is around all of it. So it's going to have the highest noise resistance. When we get to coax, it is shielded. The original shielding had it's a woven steel sort of shield that went around the system. This is one thing that they may ask, and we go to categories. Cat 1, way back when, is a voice only. When I first started, we had Cat 3 and we had Cat 3 cable and Cat 3 standards when we did this, 10 megabits per second. And most of these, you'll notice, go 100 meters. When they ask, and this is an easy question to be asked, and it's something to really know, 100 meters is most of these things, except when we get to Cat 6 for 10 gigabits per second can only go 55 meters. And typically you're going to find that as the speed increases, the data rate increases, the distance is going to decrease to some degree. And then Cat 6A, 10 gigabits per second, 100 meters. There is a Cat 7, but the book says, and they're right, it's not covered by the CompTIA test yet and training, so it's not considered here. But these things tell us what frequencies they run at, and you notice as we increase the frequency, we increase the data rate and the distances as we do these things, and the rate of change, the frequencies are going to make a difference as to how much data that we can have. And then we have plenum versus non-plenum cable, and we talked about that a little bit, I think, earlier. The plenum cable is designed to go into air spaces. And so the plenum is a space for heating and air conditioning. It's in any place, anytime, any place that we're going to have air movement. The reason we need plenum cable is when we put the cable in there, it's fire retardant and it's supposed to be self-extinguishing. It also is not as smoky, and it also doesn't have as many toxic gases. So the special fire safety requires for electrical cable label in plenum spaces, and plenum cable will be marked. They say, and let me see if I can find it, they say it'll be marked as CMP or MMP. What I've seen on most of it just says plenum on it. So if it says plenum on it, it's going to be general purpose cables marked with CMG/MMG or CM/MP. So we have the markings. Riser cable, it is special in that its conduit must be fire stopped. It's got to be fire stopped so that we don't create a situation to where fire can go from floor to floor through the riser cable. It's used in lift shafts and things like that. It's used in the vertical going from floor to floor in a building we're going to use riser cable, and it does have to be sealed so that fires cannot spread through those. RJ is a registered jack, or in position or in contact. The in position is how many positions and how many contacts, and this one down here, 8 positions, 8 contacts, and it's a 4-pair. It has 8 connectors on it. RJ48C is essentially the same as an RJ45, but it's used for ISDN. RJ45, registered jack 45, is used for Ethernet. RJ11 is the one that's used for phones, and typically phones only use 1 pair. There may be 4 pair there, but a pair, 1 pair is a dial tone and the voice. The other pair may be unused or may be used for a second line. When back in the dial-up days when we had a second line, we had there were 2 different wiring arrangements for the 2 different phone numbers that we had. The wiring standards themselves, the straight through, the TEIA, TIA 568A and 568B standards. This is the B standard here. Orange and white orange, green and white blue, blue and white green, brown and white brown. The brown and white browns don't really change a whole lot. When we have the A standard, and if we make a crossover cable, we cross 1 and 3, 1 and 3, and 2 and 6. What that does is these are the oranges here are the transmits, and the 3 and 6 are the receives. So if we're connecting like devices and you need a crossover cable for like to like, then the other end you make with the A. We make one end with a B standard and one end with the A standard. Is a crossover. We reverse the transmits and receives, so then when we go like to like, one, the transmits go to the receives, which makes it a lot easier to get the information from one place to the other. Many of the cables now are auto MDI or MDIX, medium dependent interface, which means they'll automatically detect whether you need a crossover cable or not, so you can use a straight through for much of what you do. You don't have to always do that, although it's not always a bad idea. Some of the high-end equipment switches are not always MDI or MDIX, so you need to determine if these things will auto sense or if they won't. If they won't auto sense, you're obviously going to have to make the crossover cables for yourself. Pulling cable, when we pull the cable, we can have up to 90 meters for the horizontal section. So we have 90 meters, a 90 meter section, and we go into some device. And then the patch cables can each be 5 meters, which gives us the 10. And when we have that, that gets us to the 100 meters. When you pull the cable, you should leave a loop, that's what's called a service loop at the end, so that you have a little bit of play with it whenever you want to do something with it. When you cut it, you want to cut it square, and usually we're going to use a scissors, and you really do need to get these square, so because when you put them into the connectors, if they're not square, you're not going to get connectivity from the system. With fixed permanent cable versus patch cord cables, the fixed is going to be what we run from location to location from a drop, and the reason I call it drops because they were frequently dropped out of the ceiling, versus the patch cords, which are going to go from the wall outlet to the machine, or from the patch panel to the switch. We have inline couplers here. What these things will do is allow you to extend the cable. A lot of people don't like those things because you can get some signal loss in the couplers themselves. Termination tools, we have a punch down block, and we looked at a punch down block yesterday. We have a punch down tool that goes into the punch down block to terminate the cable to what they call the insulation displacement connector. And the formats are 66 and 110. The 66 are telephone, the 110 are the new ones for data. Cable crimpers is what this thing is here. Attach the jack, the RJ45, to the patch cord. One of the things when you start untwisting these things is to avoid excessive untwisting, because if you untwist too much cable, one, you can make an ugly cable, and two, and probably not a proper cable, we're going to get crosstalk. Crosstalk is one wire interfering, the signal interfering, not noise in this case, but the signal interfering one to the other. And then we have the UTP couplers, which we kind of looked at here. Cat 6, this is a Cat 6, an inline coupler, which puts two of them together. Cable testing tools. I think before we do the tools, I want to try once again to do a video. Let me see if I can get it right tonight. See if I can find it first. And this is a little video, I think it's about 10 minutes, on how to make wire. If we had the ability, if we were all in the same place, then we could actually make the cable.
Hi, my name is Kane, and I'm here to help you. Today we're going to show you how to make a Category 5 and Category 6 patch cable. I've found in my travels that nobody knows how to
Turn it up, please.
Administrators who, like, make more money than me, run my network, and they're like, hey, I need a patch cable. Do you know how to make it? No, I don't. Here's a diagram. I learned how to make this when I was 14. You should know how to make these. They're simple. They're easy. We're going to need a Category 5E or Cat 5E patch cable. So we're going to have a length of cable that we've selected. We've got one about 10 feet right here. And we're going to need two modular plugs, RJ45. We also have our Cat 6, which we also have about 10 feet of cable here. And we have a Category 6 modular plug. Also, you're going to need an RJ45 crimping tool. These things you can pick up at your local hardware store, Home Depot, Lowe's, that kind of thing. You can find them online. They're relatively inexpensive, and you can use these to make hundreds of cables. This one's 300 years old. People will always ask you what's the difference between Cat 5e and Cat 6. And first and foremost, Cat 6 is a bigger cable. It is a higher standard of cable. It is able to shoot gigabit networks down with a lot less crosstalk, which is the noise that is made with the electricity running over the wires talking to each other, and it creates it slows down your network if you got too much crosstalk. So Cat 5e will be good for gigabit. Cat 6 is just better for gigabit networks. If you find Cat 5 cable, which does not have the E, it will not work for gigabit networks at all. Just don't try it. It's not cool. You'll be like, why is my network so slow? It's because you're not using good enough cable. Also, if you're doing this out of your home, Cat 6 is expensive by comparison to Cat 5e. We're talking like 30 cents a foot versus Cat 5e, which is probably like 15, 16. I haven't looked at the prices recently, but it's expensive to get a Cat 6. So unless you really need the higher standard cable, get Cat 5e, it'll do just fine. So we want to scar the cable sheath so we can break away the sheath and expose our conductors on the inside. So we're going to use it just very gentle. We're going to scar the cable sheath with the cable wire, or with the cutter there. And now we're just going to bend the cable, and you can see the real stress here. You can bend it, and you can put some stress on it, and it'll break away. Alright. Get the sheath exposed. And once we're here, we want to separate out our pairs, and you'll notice this little string here. This is actually for pulling back and exposing more of the cable. So you pull this back down this way, and it'll just cut the cable down. I'm not going to do it because I don't need any more than this. But you can just very carefully clip that string away. Here I've untwisted all of our conductors into our different color codes. We've got our orange pair, our brown pair, a green pair, and the blue pair. We want them to be in this order I'm going to give you right now. It's going to be white with the orange stripe, orange. And then it's going to be white with the green stripe, solid blue, white with the blue stripe, solid green, white with the brown stripe, solid brown. The next thing we want to do is we want to cut back the conductors to the proper length so they will fit nicely with our modular plug. There's a crimp on the inside of the plug that will be pushed down when you crimp it with the crimping tool. It's a lot of crimping. You want the sheath to be extended past this little space here, so it will get crimped down and it will hold your cable in place. Okay, so these conductors have to come all the way up to the end of the mod plug, and we want this blue sheath to come extend past the crimping space that's right here. So we're going to measure about where we want it, and we figure this length is good. And we want to cut, but we don't want to cut at an angle, we want to cut as straight across as possible. That's why we use these wire cutters. They explode everywhere. Now you can see a little bit of deviations, but it's going to be okay because it'll flush up in the end of the conductor. Next, we're going to very carefully, and you want to, at this point, just double check your wires, make sure that they're again in the correct order. That's white, orange, orange, white, green, blue, green, white, brown, brown. And you're going to be very careful. You want to set them inside, and I don't know if you can see it, the wires are actually being separated out inside the plug along little tracks, and they'll go all the way. Push it as far up as you can. Give it a little push. The sleeve will go up further. That's probably a good thing. You can check the end, and you'll see the copper conductors right along the end. That'll be nice and shiny. Okay, so now we're going to go ahead and crimp the cable down. You want to make sure that you don't wiggle this too much once it's in place, and you're going to slot the mod plug into the RJ45 connector on the crimping tool. Again, check the other side of the cable. Make sure you see all the copper conductors. And I usually do this 2 or 3 times. You'll see here with this push down onto the cable. It's a nice solid connection. These wires get crimped down and it pierces the sheath. This is where you can see the copper conductors are flush with the end of the connector. That's how you know you're going to have a nice, good, solid connection. Alright, now we're going to do this with a Cat6 cable. The procedure is more or less the same, just subtle differences. The things that make this cable better are also what make it harder to work with and easier to work with at the same time, and I'll explain it as I go along. The sheath is a little thicker because it's a bigger cable, and it's going to be easier to store and break open. So let's look at that. Came clean apart. There you go. Now, you can see this is a lot different. We still have the string for tearing back the sheath. We don't need it. Careful not to cut any of your wires. Now, Cat6 cable has got a larger conductor. This is a 22 gauge wire where the Cat5e is a 24 gauge wire, which means that this, for all of you Europeans, this is bigger. Just a little bit, but it's bigger. This piece is just a big glop of insulation. It separates out all of the wires and runs the entire length of the cable. So each pair, as you can see the twist here, each pair is separate down the length of the cable. And they do this to, again, eliminate crosstalk, which is the noise that is generated, the electromagnetic noise that is generated by these wires with electricity flowing through them does not crosstalk over to here. Or it does, but it's minimal. Very carefully, we want to just remove this bit of insulation because it just makes our lives a living hell. If you clip any of the wires and you can see an exposed piece of copper, cut your cable and start again, because that exposed wire will actually create more noise coming out of the conductor, or it will release more noise coming out of the conductor, and it degrades the cable, so it makes it so your speeds won't be as high as you want them to be. Also, I'd like to point out that these wires are more finely twisted together. There's more twists per cable and per conductor per pair than with the Cat5e, and that's again because of eliminating more crosstalk. So the order of operation here is white, orange, orange, white, green, blue, and it's going to be a real pain in the ass getting this wrapped around properly, but we're going to put it over there. I'm going to do white, blue, and then it's going to be green, it's going to be white, brown, and brown. And we want to flatten these out as much as possible, which is what I'm doing here. I just kind of wiggle them around until they flatten out. Again, we want to measure the length of what we're looking at. But then I'm going to introduce this little piece, and I'm going to confuse you all. This slides into the middle of this, and it's just another piece of insulation that protects from crosstalk. So we want to cut this a little higher out, and we want to put these into this connector, and they will find their way right to where they need to be, if I can get them all in there. Wiggle it around a little bit. This piece and the finished product will end in the conductor, or the modular plug, right about there. So we want this as far down as we can because we want this piece to crimp the sheath. So what I usually do is I measure out where I want this, put our little pieces all the way to where we want it, to measure the length. So that's where the end is going to be. We use our trusty wire cutter and clip right along the edge, and I'm holding this piece in place with my thumb and my forefinger, and we're going to clip off the rest of those. So now it's right flush with that, and that's what it's going to look like. Alright, we're going to go ahead and put this into the mod plug. You can see it's a little uneven, but that's okay, because once we get it in here and get it slotted into place, all these pieces, push it all the way in. You want to make sure that, again, you see all the copper conductors along the edge. Here, we're going to, again, push this all the way in, double check the ends here, crimp it all the way down. Give it a nice good squeeze, do it twice just to be sure. And there's your cable. Okay, you can see that it's crimped down on the sheath. Everything is in place. The spacer is inside. Everything is in place. Looks great. Thank you very much for watching this video. I hope you found it helpful. For all you students out there, show this to your teachers. For all you teachers out there, showing this to your students, hello. Thank you very much. I appreciate it. Everybody else, network admins, if you are watching this...
Yeah, a lot of good information in there about how to do it and the crosstalk, and you get the idea that twisted pair crosstalk is a big deal when we do these things. And once you get it made, the cable made, then we need to check it, and a multimeter can be used to check continuity. It really can't be used to load test it. It can be used to check end to end to be sure that when you did the crimp that you actually got the little pins, and I always call them little pins driven into the wire. It does penetrate the wire. It's like driving little nails into it, and it gets it there. You need to get the sheathing up under the point where the crimp happens, or they will pull out after a while. So we're looking for continuity. We're worried about shorts, incorrect termination, the wrong order. He did a good job sliding the wires in very carefully. A lot of times, particularly early on when you start making these things, you start sliding them up and the wires will decide where they want to go on their own, and we won't necessarily have them in the correct place. The split pair in this thing, when we get the pair, it actually splits the pair and it puts it into the wrong location when we do it. The wire testers themselves are something that can really help you out. We have reversed pair. The conductors in the pair have been wired to different terminals from pin 3 to pin 6 or pin 6 to pin 3, and that's what a wire tester will tell you, whether it is actually wired correctly or not. Cross pairs, the conductors from one pair have been connected to pins belonging to a different pair. For example, pin 3 to 6 and pin 1 to 2, which is kind of like a reverse pair. Short two conductors are joined in the same point. We get two conductors in the same hole, and then they get shorted out when we do the crimping of those things. A toner and probe is used for cable testing. It's a tone generator, and then a probe we use to go find the cable. If you have cable that you don't know exactly where it is, then a probe is one of the things that we're going to have to use to find them. A time domain reflectometer is something that actually will test for faults down the cable, and it'll tell you how far down the cable the fault is. First time I ever used one of these things was in the early 70s. I was working on A4s, and to change the engine on the A4 you had to take it apart in the middle. And I was an electronics technician, and they take all of our, at the time, coax off, and then when they put it back together, it wasn't always right. You had to needed to find where the issues were, and those issues we found with a time domain reflectometer. They were huge then. I looked them up on the internet today. You can get them, a low-end one you can get for about $150, $200, or you can go up to $3,000 or $4,000 on them, depending on what you wanted to do. It's like most test equipment. Most of this test equipment is pretty specialized, so it except for the wire testers, so they can a lot of times charge what they want. A line tester, a butt set, something that a lineman uses to test the phone lines themselves. This is the cable testing, and these are not the order that you would go to make an RJ45, obviously, but this gives you an idea of what each of the faults are. The correct, all the pairs go pair to pair, the solid blue to solid blue, blue and white to blue and white, and on down. Crossed pair here, we have the green and white get crossed with the orange and white, and orange. So that's what a crossed pair is. A reversed pair is within the pair, the two wires get reversed. And then a split pair, they again get into the wrong area here. We have the green going to the brown and white going to green, and over here the brown and white going to green, green going to brown and white. So what some of those terms mean, a visual here on what they do. Cable testers report attenuation, noise, crosstalk. Sometimes depending on how much you pay for these things, it is going to affect how much they actually do. These advanced testers can give you some really detailed information about what's going on. And when we get into the gigabit and the 10 gigabit, you're probably going to need something like that to test it, not just simply a tester to be sure that we've got all the pairs correct. And when he talked about if you nick the cable, start over. If you nick the cable, start over. So we have these things. The distance limitations, troubleshooting these distance, we do have distance limitations. We've talked about attenuation earlier. Attenuation, if you recall, is when the signal strength goes down as the distance increases down the cable. Insertion and insertion losses, if the cable's not made right. dB losses or decibel losses, and these are, dB is what the losses are actually measured in. Crosstalk near end and far end. Near end crosstalk is at the transmit end and far end's at the receive end. And then they have a term called alien crosstalk, which is something that happens when the cables are close to each other. Crosstalk can be caused by a bad connector, and when he undid the wire, a lot of times people don't get the wire all the way up into the connector to where the sheathing gets crimped down and you get wires there. If you have excessive unwinding of the wire, that can also cause crosstalk. Electromagnetic, EMI, and RFI. RFI is radio frequency interference. EMI can be caused by, usually caused by electrical motors, maybe fluorescent lights, things like that. RFI, RFI is radio interference from transmissions. The sources, heavy machinery. I was doing a question today, and it was in the doctor's office. They had a CT scan. I didn't read the question well enough, so I answered it wrong. But equipment that radiates electromagnetic fields are going to affect these things. And if you get into an environment where you have heavy machinery, instead of using these things and worry about crosstalk, then that's where we would really be dictated to use fiber optic. RFI, microwave ovens, anything that radiates would do those. And then alien crosstalk, we talked about cables too close together. Cable placement, you want to keep the cable away from all of the things that can cause the interferences. Fluorescent lights are one of the things that can cause you issues with the cables if it's too close. If you lay it across a fluorescent light, it's going to affect your data rate. It's going to put noise on the system. They really do some not good stuff for it. RG, radio grade standards, we're talking about coax in this case, and a coax is shielded. If you look at this thing, it has a copper shield around it, an insulator, and then the core conductor, and then it has a casing around it. We had two different types of legacy, and the legacy coax, what I said earlier, if you see, hopefully you're not ever going to see coax, but we have Ethernet, we have thicknet, and thinnet. Thinnet is the stuff that is pretty easy to work with. The RG58, which is what this would be. The thicknet, well, I've seen it one time, but what people call it is like a frozen water hose. It's about that size. It is very thick. RG6 for cable TV, and RG59 for older CCTV installations. And the BNC, when you see, and they frequently want you to identify a BNC. A BNC is the twist-on connector. The F-type connector is the threaded connector here that used in, at least used in my cable system. And the BNC coupler is similar to the RJ coupler. It's just going to be a solid piece with the connector points on it that allows us to put two BNC sections together. Serial interfaces, we have in the networking world two types of equipment: the data terminal equipment, which are like the computers and the equipment that we use, the terminal equipment that we use, and then the data circuit terminating equipment. Modems would be one of those. When we put these things together, we have to connect with them, or we do communicate with them, typically using a serial port. So we have straight through, and the modem, we'd have a null modem. If you went from one computer to the other, you'd have to connect it with a null modem. The standard that's used for the serial interface is the RS-232 standard, and the DB25 pin on PCs and a DB9 connector is what works on these things. If you have the big serial port, the DB25, we have the DB25 pin here, the 25 pin here. This is the DB9. This one would actually go in here. This is a Cisco cable that's designed to connect to the serial port on a laptop or a computer. And if we have the 25 pin, we have to have the converter, and then connect to the console port on the router so that we can configure the router. And the console, we talked about straight throughs and crossovers. These are console port cables or rollovers, which means that we go 1, 2, 3, 4, 5, 6, 7, 8, 9, and then the other one is 9, 8, 7, 6, 5, 4, 3, 2, 1. You actually roll the cable over completely. If you're making it, you make one of them with the RJ45 tab up and one with the RJ45 tab down, and then you'll have a rollover. Serial cables are also used for WAN serial links. If you remember Ethernet, and we go back to the cable, Ethernet goes right now about 100 meters. And fast Ethernet, we don't have to worry about collisions because we're in a switch and we can keep repeating it from location to location. WAN links, serial links allow us to go at a longer distance, but typically when you have a longer distance, you're going to have a lower data rate. As we continue to increase the quality of the connectivity and the quality of the materials, the data rates have increased and increased and increased. If anybody remembers dial-up modems, 56K was a wonderful thing at one time. And now we're talking about getting, what, 30 or 40 or 50, 60 meg and up to gigabit into the house if you have a, if you're willing to pay the price and you have fiber coming to your house. The fiber optic cable itself, and a lot of times they ask these questions, we have a core, and the core is actually where the fiber is. Around the core is cladding, and the cladding helps keep the light in, and then a buffer around it, and the buffer is going to be some sort of a plastic cover around, and then we cover it. But when you make these things, you strip off the cladding and it shows, and then you put it into a connector, and they usually have 4 or 5 connectors that they want you to identify also. You polish the end to get it smooth, put it in the connector, and then you basically glue it in and polish it so that it makes contact with the other end. And this is, remember, is a light signal that goes through here. These things they call total internal reflection that keeps the light in. We have single mode fiber and multi-mode fiber. Single mode is much smaller, is the smaller of them, and the smaller core, and it goes much longer distances. So when we do that, when we go to long distances, it's going to be single mode, and it uses more expensive optics, more expensive injections. It might be a laser instead of an LED that puts the signal onto the system. Multi-mode fiber, cheaper objects, shorter range, and it is going to be the thing that we typically are going to use inside of our network, would be the multi-mode. You make them about the same. The multi-mode is bigger, I think, that probably about 65.5, I think, is a single mode. Let's see if I can find it here. Let's see. The multi-mode is early is 50 microns. The cladding 62.5 microns. It's 62.5 or 5, and then the single mode is 8 to 10 microns, so you can see that it is much smaller than the multi-mode. Installation issues, the only things you have to be careful about bending this stuff, and it is glass and it will break, and I found out it was glass first time I made it when I cut myself with it. Yep, it's glass. They make a plastic one that's for use in like cars and airplanes that resists the shock better, but it's much shorter. It's a very short distance. But you have to be careful when you install it. The bends that you put into the fiber can affect it. The connectors, the ferrule physical contact PC, ultra physical contact PC, and angled physical contact PC. The ferrule is the thing that's going to hold us together here. How much contact are we going to have on these systems? And these are just going to be the different ways to do the installation. The physical contact, I'll read this out of the book. The faces of the connector and fiber tip are polished so that they curved slightly to fit together better. Ultra-physical contact means that the cable and connector are polished to a higher standard with PC than with the PC, with the physical contact. And the angle, the faces are angled for an even tighter connection. We don't solder these things in, they just go in and the interfaces touch. Four of the different connectors here, and you probably will be asked to identify some of them. The straight tip is obviously a straight tip connector. FC, the ferrule, which is not pictured here, it's kind of like a bigger version of this. The subscriber connector, the SC here, Lucent connector, and mechanical transfer register. All these are different as the systems have progressed over time. The connectors have changed. One of the things that you want to be sure, these connectors all come with covers. When they're not in a receptacle, you want to be sure the cover's on, because if the tips get dirty, then it's going to affect your transfer, and they do need to be cleaned occasionally. This is a picture that I found. This is the FC connector, the ferrule connector. I said this is kind of like a version of this but bigger, and it is. Different connectors. Interface converters are things that are media converters. They're going to change us from one RJ45 here to fiber. So in this one, we probably have our machines coming in, and this would be the port that takes us back to the NOC. A media converter down here is just a straight media converter, fiber optic to twisted pair. When we have fiber optic, you notice there's two connections here. You have an in and an out, just like on the wire we have an in and out. We have a transmit and receive. They're just that they're all together in a single connector. Some of these, if we use a straight tip or something like that, we would have multiples of them. Some of these, right here, the LC has got both connectors in the same frame. So depends on what it is, and this one, the MTJR, has both connectors. You can see that the two fibers are going to come out in these locations, if I can get there, here and here. So different ones, different times when we do these things. One media type to other. They're usually powered with single mode fiber to Ethernet, multi-mode to Ethernet, fiber to coax. If you're using coax, and I guess maybe if we're using it in the TV system. Unpowered, single mode to multi-mode fiber. We have these things. Troubleshooting, we have attenuation. An attenuation against the loss of signal, dB loss. Fiber has attenuation just like copper does, but it's not nearly as severe. So you can usually go farther with them. Also, we don't have crosstalk, we don't have RFI, we don't have EMI with the light signal. So you can have a much lower signal when you repeat it. Remember, since it's binary, 1 or 0, off or on, it's really easy to, as long as you don't have the noise, as long as the signal's greater than the noise, you don't have a whole lot of decision making. It's either yes or it's a no. And each of these, again, have distance limitations, cable and fiber type mismatches, When we get into the cables, if we have a mismatch, the cables all have resistances as well as whether they're whether they're core solid wire or whether they're stranded wire, and the gauge as we talked about earlier, but they need to all be the same resistance. When we moved into a building a few years ago, and this was coax, this was a lot of years ago, 20 years ago, there was a lot of coax already there. And we decided, and we were using coax because they told us to for whatever reason. I guess it was cheap. We decided that we would use the coax was there. Unfortunately, when we got to doing things, the coax that was installed in the building was a different resistance than the coax we were using, and we could sometimes get connectivity and data transfer and sometimes not get those. Let's see, wavelength mismatches, connector mismatches, bad fiber cable, dirty connectors are one of the things that kind of common, I guess. The faulty SFP GBIC says when you're troubleshooting a switch or a router, check that any plug modules installed in the appliance are correctly seated. So many of these things, and let's go back to the switch. Let's go back to the switch. These are plug-in modules typically they can take out. You want to be sure that the module is actually properly seated in the system. Dirty connectors, if they don't have the cover on them, then that can happen relatively easily, and they do have to be cleaned. And this is a fiber thing, obviously. Bend radius limitations. If you have excessive bends too short of a radius on these things, that can affect what goes on with the system. So in this module, we looked at the different types and the properties of the different cables, connectors, twisted pairs, fiber, and coax serial cables. I talked about wiring standards, and we talked about wiring standards in the video. We looked at pictures of and talked about media interfaces and media converters when we go from one type of media to the other, and a little bit about the proper tools for the network hardware installation and testing. So it's time to do the questions, and then we take a break. What is the measurement standard for wire thickness?
Gauge.
Gauge. AWG, gauge. Yeah. What is crosstalk?
The magnetic field interfering with each other.
Signal linkage, yep.
Flux.
What? Huh?
We used to call it flux.
Yes. Yeah, exactly.
Yeah, but it's the magnetic fields that are interfering.
Yeah.
Yes. Yes. Got to turn my volume down. What categories of unshielded twisted pair are certified to carry transmissions faster than 100 meg?
Cat 6.
Yeah. I was trying to go back and I messed up.
5V is still 100 megs though, right? It's just better shielded.
Well,
So
let's see. Let's see, we got 5E, and let's go back to what they said. We had this table back here, way back at the beginning. Here we go. 5E can be 100 gig.
Oh, 5 is.
5E is a better cable. When he talked about that 6 is a little bit more, the 5E and to me the 5E and the 6 were always very difficult. They're stiffer, the wire's bigger. I always thought it was more difficult to work with, but that's just me. True or false, CAT standards apply only to wiring?
True.
Really?
That'd be a trick question.
That'd be a trick question, but we have all these other things. What about the receptacles? What about the connectors that interconnect these things? They all have CAT standards too. Why is plenum rated cable used when cable is running in an area of the building where air is circulated?
What was the answer though? Was it true or false?
It's false,
False.
Okay.
because we also have to use the connectors and the interconnectors. All of them have standards. And really, when we get, it's not a CAT standard, but when we increase the speed, we're going to have to change the switches out too. So why do we use plenum rated cable in an area where building air is circulated?
Is that for fire resistance?
Fire resistance. Minimal amounts of smoke, and it is fire resistant. It is supposed to help put its own self out.
Higher combustion.
Yep.
Level.
100 base T transmit pins 1 and 2. What color are the wires terminated to these pins under the A and the B standard?
Orange or green.
Yeah, orange and white orange, green and white green for the B and the A. The orange and white is the B standard, and the green start with the A standard. And when you do a crossover, you swap pins one with 3 and 2 with 6 to make a crossover. I mean, at one end you do the orange and white, and then you swap 1 and 3, 2 and 6. Patch cables are vulnerable to failure because they frequently trail from the PC to the wall socket, and people trip over them and do all sorts of stuff. What bit of equipment would you use to check that a cable is physically intact? Electrically. I would say physically. I'd say electrically intact.
It's not the ohm meter. I forgot the name of that little thing.
How about a cable tester?
Cable tester, yeah.
Wire map tester.
Wire map tester. Yeah, they got a lot of different names for those things.
What's the name for the test?
Cable tester is what they give.
Okay.
What this publisher gives, what they're doing now. Cable probably would be cable tester.
That's typically a wire map tester or a little handheld TDR that you test the CAT rating.
Yeah.
When you're after you test after installation.
Yeah.
Yeah, I've seen them. I've messed with them before, but I've just thought it was a cable tester. I just never knew what the actual name was.
Which pins are used for the receive pair under 100 base T? Which pin numbers are the receives?
RS232?
No, on the RJ45. I'm just reading those here. Which are you got 1, 2, 3, 4, 5, 6, 7, and 8. Which ones are the receives? Say again?
Transmits 1 and 2, 3 and 6 is receives.
3 and 6 are the receives. 1 and 2 are the transmits, 3 and 6 are the receives.
Wait a minute, repeat that one.
Hence, those are the pairs that reverse between the
Yeah.
568 A and B to make the roll.
Okay. In this, the pins 1 and 2 are the transmit, 3 and 6 are the receive.
Right.
So we have the transmits and the receives there.
So if they're only using 4 cables,
When we
what are
get,
the other ones for?
well, originally what they thought they would do was use 4 of them for data, and then they would have some pins available for a phone, and so they'd only have to have 1 connector wired, but that never really worked out. With the newer standards 6, all 4 wires, and 7, all 4 wires are used for signal. So only in the 100 meg, when you get into the gigabit, you use all 4 wires.
Oh,
Or all eight wires.
Eight?
Yeah.
Okay.
All 4.
You got PoE stuff in there.
Yeah. You use all the wires. How's that?
Yeah. All 4 twisted pairs.
All 4 twisted pair. There we go. Thank you. You saved me. What cabling faults would a wire map tester detect?
Something I left off their list. Opens.
Shorts,
Reverse, split, and
and
cross.
transpositions, all those things. Reverse cross pairs. So we have reversed and cross pairs here. It'll detect all of these things. All the mistakes that we can make, and when you start making them, my fingers always wore out, because when he started making those things a little less stiff, you got to do a lot of bending to do that and get it nice and smooth. He did a nice job of making those cables. How would you test for excessive attenuation in a network line?
TDR, I guess. Right?
Yeah, what we're going to have to do is inject a signal. TDR would do it. And that's here. We do attenuation, insertion, and see what kind of a dB loss that we have. And the TDR would tell us that also. What's the dB loss? The dB is decibel, and that's just what it's measured in. And in decibel, 3 dB is a 50% change, either up or down.
What was their answer?
Measure the insertion loss in dB using a cable tester. Although, yeah, that's going to be a pretty fancy cable tester. Some of them won't measure dB.
Yeah. TDR might be overkill.
Yeah. Yeah. Well, TDR is the thing that's going to tell you precisely, good, bad, where any problems are with the system. If you have any sort of a break, any sort of a resistance, it's going to come back and show you exactly where it is down the line. But they're not, I mean, they come down in price. Some of them aren't that expensive, but they're not cheap. They're a lot more than my little $15 off of the internet cable tester, which tells me that, yes, I have a straight through or a crossover or the cross pairs and all those other things. This one I didn't do, so I'm going to tell you the answer. What is the reason for making power sum crosstalk measurements when testing a link? And the power sum measures are when you use all 4 pair, as a gigabit and a 10 gigabit Ethernet do. Which cable types are made of a solid core of copper surrounded by insulation, by braided shielding, and an outer cover? Coax. What surrounds the core? There we go. What surrounds the core of optical fibers in a fiber optic cable?
Cladding.
Cladding. Yeah. It looked. I know.
I heard they're getting better with those as far as like the bends.
Oh, they are. And all of these media, it's just like it's just like the twisted pair. When years ago, and I don't want to be that old, but I'm getting old. But when I started, Cat 3 was the standard, and then it was Cat 5, and then we keep moving up with how fast we can go. The original one, the first one that I had, 10 meg was it. That's it. That's all you're going to get because it was Cat 3.
Larry, I think Cat 3 didn't even exist.
When you started?
Well, I mean...
Oh, no, don't tell me that.
20 years. Well, I did go back 20 years. But the thing is, we were doing twisted wire Ethernet in the 80s, the late 80s.
Yeah.
And then they didn't even come up with categories until 88 or so, when all of a sudden some cables weren't working.
Yeah. And they for a long time it was Cat 1, 2, 3, 4, 5. 3 was the first one, I think, that did data. Cat 1 was voice only. Cat 3 was data, and 4. I don't think 4 ever really existed. It may have. They never talked a whole lot about it.
I'm not sure what it is.
Yeah, and then 5 was.
I'm a dinosaur.
Yeah, 5 was the way they got it going. What type of fiber optic cable is suited for long distance links?
SMF.
SMF, single mode. What?
It's one, I remember you can use multi-mode for single mode, but you can't use single mode for multi-mode. Is that correct?
Yeah. You really don't want to mix them, because if you do, you're going to have problems. Single mode fiber is basically a single frequency, and multi-mode allows us to have multiple signals on a single piece of fiber.
Yeah, I remember that.
More pulses.
Say again?
More pulses, more digital.
More pulses, yeah. And
they're totally non-compatible.
Yeah, exactly. And they really are very different in size too when you start working with them. What device enables fiber optic cable to connect to a switch?
Oh, it's keep going.
Parts of media.
Media, how about media converters?
They
say an interface converter, but an interface converter, media converters. The interface converter would be the interface here on this thing.
That's what those things were. When I used to mess with cell phone towers.
Yeah.
I used to go through and check those out.
Uh-huh. Questions? If I confused you enough in this part? You ready to take a break?
Yes, can I ask a quick question though before we take a break?
Yeah, what? Now say again? Yeah, go ahead.
Let's see. The question I want to ask is, are we going to get all the questions that you asked after every review, or are you just taking those out? I mean, I don't know what I'm saying, but
You want me to make you a copy of them? Is that what you're saying?
yeah, just so
I can do that. I can do that. Yeah.
Well, they're in the book.
The questions are, and well, I guess the answers are too. Are the answers at the end of the book?
I don't need
The answers are at the end of the book.
Yeah, that's what I thought. Yeah, I think the whole thing, Tamika, is at the end of the book.
Okay, because that book I got, it's not.
Four in depth.
Okay, yeah, because she's got a different one than you guys. You've got a paper one, right? And everybody else got a digital, I think.
Yeah, but that paper one is not good. I got the digital now.
Okay. Okay, yeah, I can make copies of these. I'll go back and do that. That's not a big deal.
Thank you so much.
Okay. Other questions? Let's take a break. Let's come back at about, let's say 25 after the hour.
Yes, sir.
Let's talk for a few minutes about wireless and installing wireless networks. You probably already have done that in your house, and what we do commercially, not all that radically different than what you would do in your house or in your neighborhood. I don't know about yours, but mine's got a whole bunch of machines, a whole bunch of wireless networks. Running around here and trying to find a clear channel has been not easy, and then people change the channel and it becomes not clear anymore. So the objectives of this one is distinguish between the different IEEE 802.11 Wi-Fi standards. And Wi-Fi wireless is just like wired. As we go further into the world of networking, time-wise, wireless gets better and better and better. And it's becoming a real, I guess, popular standard, popular to use because it has gotten a lot better. We're not back in the 10 meg world anymore. Distinguish ad hoc, infrastructure, and mesh topologies. Perform a site survey and understand issues impacting a site design. And site surveys are kind of interesting to do. Troubleshoot wireless connectivity issues. So we'll look at those things. And I noted, you noticed right straight off that we've changed the standard here from 802 to 801 in this slide. But 802.11 Wi-Fi is the standard that we use, and it uses a radio carrier. In the 802.11, we encode data on a radio transmission instead of on a transceiver into a piece of wire. And we use modulation for these things. It uses a number of modulation schemes, most of which are either quadrature amplitude modulation, QAM, which I found a picture of that and I put it up because it's pretty confusing, or phase shift keying, as well as other modulation schemes. And Wi-Fi standards use different carrier methods when we do these things. And we're going to have two major frequency bands, the 2.4 gigahertz and the 5 gigahertz. When we started doing these things in the world of Wi-Fi, both of these standards came out at about the same time. The 2.4 gig, which probably was the not as attractive one, won because 5 gig they couldn't find the materials to make the chips to actually sell the 5 gig for a long time. 5 gig has always been a higher speed. It started out at 54 megabits per second. And in the 2.4, when we got to G, we finally got to 54 megabits per second. So the frequency bands, the 2.4 gig and the 5 gig in them. It's CSMACA. We're going to use collision avoidance in this thing. It's like shared Ethernet, but the collision avoidance is the media access. And we have to have that because if we have an access point and we're going to have a machine here and a machine here and they're at maximum distance, these two machines don't even know that they exist, so there's no way they're going to be able to detect collisions. So what we use is a collision avoidance, and what happens is this guy wants to send some traffic. It goes to the access point and sends an RTS, a request to send signal. And then it sends back a clear to send signal, and then the data gets sent. And when the data gets sent, it has to acknowledge every frame. Unlike when we did Ethernet, we had a window where we could send several frames, multiple frames, depending on how big we made the window size before we did an acknowledgement. All of these things tend to make wireless a little more accurate, but also much slower because we can't send a lot of data at the same time, and you have to go through that request to send and clear to send in order to get data on the media in the RF spectrum. The 802, this is a picture of the 802.11 channels, 11A channels, excuse me, and we have 36, 40, 44, we have a lot of channels, and then there's a break. There are actually two ranges that we have channels here that can be used. What this represents down here is what's called channel bonding, so that we, instead of doing single channels, we can put channels together, and the more channels that we can put together, the higher the data rate that we can get out of here, because we have, this is a true bandwidth, how much frequency that we have to use. We have this much space to put data on. The bonding, I think the N standard is the first one that we actually were getting bonding with, and it allows us to get a higher data rate. If there are other systems in the area that they receives, it'll minimize the channel bonding so it won't interfere with the other systems. The 802 standard ratified in '99, 5 gigahertz frequency band, higher frequency, and when we go to higher frequency, the higher the frequency, the shorter the distance it's going to go. The signal, the higher frequencies get absorbed quicker than the lower frequencies do. It's 23 overlapping 20 megahertz wide channels, and it uses orthogonal frequency division multiplexing. Frequency division multiplexing, where we put multiple signals and when we use the frequency to do that. Up to 54 megabits. The good put, much lower. Good put is how much data you're actually getting through, and the good put goes back to all of these things that slow it down, the acknowledgement of the CSMA-CA, the clear to send, and the request to send and the clear to send sorts of things. This is the 2.4 spectrum, 2.4 gig spectrum, and you notice that we really only have 3 clear channels. Although we have a whole bunch of channels, they interfere, they overlap with each other. So we have channel 1, 6, and 11, and that's what your system at home should be on one of those channels. And you can get, for your phone or your tablet, free software to tell you who's on what channel and what the signal strength is, and you want to be as far away from the other strong signal as possible. What we wind up here with the channels are 20 megahertz or 20 gigahertz channels, and these also in the N standard allow channel bonding as long as you have free reign to the system. If you have a situation like I have where I'm not getting any bonding because there are too many other signals around that say no, don't do that. This one shows 14, but these are not used in the US. These are the channels that are available in the US. I have one that keeps recommending I use channel 14, which would be really good, but it's not authorized for use in the US. The 802.11b, this is BG, but the B was ratified in 99, 2.4 gigahertz, and it was 11 megahertz. And you're not going to get that because of all the other things that goes on. And these data rates that they talk about are when you're pretty close to the access point. The farther you get away from the access point, the slower the data rate. And you may have experienced that in a hotel. You get free Wi-Fi, but you're so far away you can't get anything. 11 channels in the U.S., and again, but only 3 non-overlapping are available. The 11B used direct sequence spread spectrum, which I always have trouble saying, DSS. What that means is that part of the signal sent on one frequency, the next one another frequency. They call them chips. So you get a chip on one frequency, and it goes across the entire spectrum of these frequencies. So we have chips on multiple frequencies, which allow us to have a little bit better maybe data throughput because we're going to be looking for clear channels on those things. The G offered up to 54 megabits per second for 2.4 with backward compatibility to 11B. One of the things that does happen if you configure an 11B system, and there probably aren't that many left around anymore, but if you put an 11B on an 11G network, then it backs the network off on a lot of the internal operations of the system to the 11G speed. So if you have G systems or G equipment, you want to set it up so that it only uses 11G. The 11N standard was ratified in 2009, and it uses both the 2.4 gig and the 5 gig frequency. If you have one of the higher ends, some of them, and I had one time that only operated at 2.4 gig because it was one of the inexpensive ones. It's called a multiple input, multiple output, a MIMO system, which means that we have multiple antennas that we can, multiple input, multiple output. Instead of having a single signal, we can have multiple signals going out on this system. It can use channel bonding, and these are 40 megahertz, which means that we're putting two channels together, or two of the individual channels together. So we can go up to 40 megahertz on these things, up to 150 megabits per stream over the 40 megahertz channel. It does have a longer range. It was almost double the other standard, and range on these things is going to be determined by what's in the way. If you've got a rebar enforced cement wall, you're not probably going to go through it with any of the standards. So longer range, and all the ranges that they give on wireless are open. There's no impediments at all. When you get into a room, lots of things can happen to your wireless signal. It can get bounced around. It can get absorbed. Even if water is a big absorber of these things, and even if you try it out in an empty room, and this is one of the way back when was a problem, in a planning problem, that you were going to have a conference, you're going to have, I don't know, 500 or 1,000 people in an auditorium, and you went in and set up the wireless, and it worked great, and then all the people came in and it didn't work great because the signal got absorbed by the people. We humans are a lot of water, and water really absorbs these signals. Longer range compatibility modes, high throughput mixed mode, 11A, 11B, 11G. So we have some compatibility capabilities with it. And since it uses both of the frequency ranges, it can use the A's, the B's, and the G's with these things. And then we have the non high throughput mode, where we're not going to have any compatibility at all with any of these guys. The 802.11ac is the latest standard. It uses the 5 gig frequency only, and the data rates are similar to gigabit Ethernet theoretically. This 4x4:3 is with an 80 megahertz channel with 1.3 gigabits is the nominal data rate. 80 and 160 megahertz channels, so we've got much larger channel bonding, and up to 8 spatial streams. And the spatial streams is the number of antennas that we're going to have. The spatial streams are the number of multiple input, multiple out, simultaneous signals that we can have with these things. You have to find somebody that makes one with that number of spatial streams. The other thing that these things can do is to send a stronger signal in a particular direction if you have users there, so that we can have better connectivity with the wireless. And one of the things that if you have multiple users in one location in one area, then they're going to share that bandwidth that comes up to that area. Ad hoc wireless or peer-to-peer. If we have two machines with a NIC, we can set them up in ad hoc mode, and they can create their own little wireless network. An infrastructure is one where we have an access point of some type on it. And this shows a relatively complex one. We get the patch panel, switch, the internet. The access point out here, actually I guess that's not all that complex, is it? The access point out here with these guys, and it connects into the switch. You can make your home router an access point if you desire. Some of them have an access point mode, but they're designed to route. They're designed to take things in on the switch. We probably have a 4-port wired switch, a WAN connector, and then we have the radio signal that goes out to our wireless systems, and they all come in and work together. The objective is typically to get to the internet. The objective for the access point is to get onto the network where we can get resources and get to the internet, obviously, here. If you connected your network switch, or if you connect it into the switch portion instead of into the router portion, you would connect everything to the network, and you can get addresses if you want to extend your network. So the infrastructure stations connect via base stations, the access points. This is for a larger infrastructure, and what they don't show here, they show a switch, but it's going to be a controller. We're going to have a wireless controller, which will be a switch, and it's going to configure and manage the access points for us. An access point plus attached stations is a basic service set, and these are all terms that on the wireless tests they like to ask. I don't know if they'll get that deep on this one or not. The MAC address of the access point is the BSSID. So the BSSID is the MAC address, and everything has a MAC address here. Each wireless LAN has a service set identifier, an SSID, the name that we see broadcast, and that comes out in a beacon frame. And the beacon frame doesn't just send the SSID; it also sends all the capabilities of the wireless access point. It's a huge frame. It tells what kind of security it has, what its data rate is, whether all sorts of stuff. It has information, lots of information about it. Mesh is a self-forming network and path discovery. This is a wireless setup, and the advantage to it is we can put a bunch of mesh access points out here, and they will automatically connect themselves to the together and form a network. At some point, somebody's got to be connected back to the wired network. One of them has to do that. A wireless distribution system would be one of these things. We would distribute things wirelessly instead of having a wired distribution system. And a wireless bridge would be if we had two buildings perhaps, and we wanted to connect them together. We could set an access point up here, and we probably would use a high-powered antenna to talk to the other building. This would be handy if you can't have a wired connection. One of my examples is always, if you want to get across the Grand Canyon, what would you do? You're not going to lay wire. You could put a wireless bridge in there, and then these are going to come down and connect to the rest of your network. And we've put our two network segments together here by doing that, by using a wireless bridge. And typically these are going to be outside, and they're going to be higher powered antennas, a Yagi, a focused antenna, or a parabolic antenna when we do those. Wireless controllers are wired systems, or systems that are on the wired network that have wireless access, that manage hundreds of access points, up to hundreds of access points. It's appliance software solution. They configure what are called, it's called a thin or a lightweight access point. What we have with the configurations that we can manage on our access points is a thick access point. What I found interesting was in Cisco, when you upgrade an access point, you upgrade it to lightweight. You take away your ability to manage it and make it a lightweight. It's managed by the wireless controllers. And the lightweight access point protocol is the protocol that's used to do these things. VLAN pooling, multiple VLANs when we do these things. And most of these systems are going to use power over Ethernet so that we can set them out in places where there are not power plugs. We're going to send the power to them via Ethernet cables. Wireless site design, the SSID broadcast, whether you want to turn it on or off. If you turn it off, that's okay. It's not going to keep it from being broadcast because it's going to be in the beacon frame. And if you go down to, and you have to use a Linux system in wireless in order to put it in promiscuous mode, you cannot do that with a Windows system. But when you read the frames, you can read the SSID within that. So If you don't broadcast it, it's going to make it invisible to probably your neighbors, but it may not help you if somebody is dedicated to getting the system on. Roaming distribution, what roaming allows, if we have multiple access points, if we go from one to the other, it automatically switches it based on signal strength from one to the other. Say, well, I can do that just by going from one access point to the other, one home office access point. And you can, but you have to reestablish the connection. What roaming does is carry the connection that you initiated from one access point to the other, and that's where the wireless, where the controllers come in. They get you authenticated, and they allow you to have access to these things. Device density is how many devices we have on an access point, and access points don't have unlimited service. They have the number of machines that are allowed on these things. And if you get on them, somebody gets on them, if you get a download happy person on it, they're going to slow things down for everybody else, because generally once you get access to it, you kind of keep access to it. So one of the best ways to have a denial of service for wireless is to go download a big movie or something like that legally. The mobile device types we have, these are things that you probably have. Some or all of these: a laptop or a computer. Cell phones, and cell phones are more than cell phones now. They're not phones, they're little handheld computers. Tablets, gaming devices, and media devices. The bandwidth per device, uplink and downlink, how much are we going to give these things, and then the signal strength and the data rate are related. The stronger the signal strength, the greater the data rate, and it's the farther we get away, the slower the speed is going to be, the worse the connection is going to be. We were at a hotel not too long ago, and we were the last room down, and my phone had a higher data rate than the wireless access point did, than the wireless did in that signal, in that hotel. The antenna types, most of these things have omnidirectional, which means that we're going to have a signal coming out around the entire, I can't really do that, can I? Around the antenna. We have horizontal and vertical polarization in these things. That's which way the signal gets sent out. We also have some high gains. A Yagi is like a TV antenna. I didn't get a picture of one, but it's one of the ones that has different size elements that go from large to small. And then we have the parabolics, which you've seen. The parabolics, these focus the signal so that we can get a higher signal going in the direction that we want, so that it's going to extend the range for us. The omnidirectionals sends the signal out in all directions, not going to be as long a range as the other ones are. The MIMO, multi-user, MU-MIMO, multi-user, multi-in, multi-out, beamforming, and the beamforming allows us to send a stronger signal in a direction of the user. If we had a user over here, we can focus the signal to go into that direction. The number of antennas are going to dictate how many conversations or connections we can have going at once. So the more antennas, the better the data rate is going to be for these things. It sends a signal more strongly, the beamforming on one axis. So if we have a signal in one direction, it says it's a primitive sort of switching. If we had two users in one of these directions and we sent the signal up here, these two users would share the bandwidth that is going in that direction. All of these changes have tended to make wireless data throughput better, the range greater as we go through these things. For all you Colorado guys, there was somebody out there in the Denver area decided that he wanted to be able to get his wireless signal at his favorite bar. So he set up some of these focused antennas and got to an illegal power and was actually able to get a signal from his wireless. The only problem was he couldn't get back because he didn't have that kind of power to get back. So you're going to have, this is a two-way street. If I have a very powerful wireless access point, it may or may not do me any good. If I have a low power device out here that's getting the signal, its signal may not get back to the access point. Coverage and antenna placement. What you don't want to do is put the same channel side by side. If I have channel 1 here, the next point I want to do 6, and then I'll do 11, and after that I'll go back to 1 because those are the only true unique channels. If I put 1 within the range of 1, they're going to interfere with each other. So we need to set the systems up so that we separate the channels as much as possible when you do those. Determine the number of users to support and the usage patterns and environmental obstructions. Environmental obstructions, walls, interference sources, microwave ovens, game controllers, lots of things run on the 2.4 gig. The 5 gig, or 2.4, it's 2.4 meg. The 5 gig, or 2.4 gig, I'll get it all right here in a minute. The 5 gig doesn't have as many devices running on it, so if you can use the 5 gig range, it's probably going to be better for you. Use non-overlapping channels on these things, 1, 6, and 11, for co-channel interference, and separate the channels. Modern access points use frequency bands to support legacy clients. We have the 2.4 gig for the 802.11 B, G, and N, and then 5 gig for the 802.11 AC. The SOHO wireless routers versus the enterprise. The small office, home office are adequate for most of the things that we do. Enterprise routers allow things like roaming, where you can go through the whole campus and never have to log off and log back on. Lightweight access points managed by controllers, so that you manage all of them simultaneously, and you download or upload the configurations to the lightweight access points when we do those. The site surveys and heat maps. The heat map is a map of the intensity of the wireless signals. These are always good things to do. There's a number of free applications that you can get to do that. Insider, INSSIDER was always my favorite. I tried to get it for my phone the other day, though, and for the phone it's a pay. I don't know if it still is for a tablet or not, or a tablet for a laptop or not. It used to be free. It gives you a very good look, but there are lots of things, lots of applications that allow you to plot signal strength for your wireless access points. It says look at the floor plans and the rooms to identify obstructions, walls, filing cabinets, books, those sorts of things. And plan the cells to provide good coverage of the area. You may need to put some of them closer to others in order to get the coverage. Once you get them in place, go do a survey to see what the signal strengths actually are when you go from one to the other. Wireless survey tools, and there are some of them out there where you're going to identify the signal strength. You also want to identify all of the other interfering signals that you can find, so that you know where to put them, where to not put them, where the interferences are. If the interference is yours, what sort of things you're going to use. And then the troubleshooting, signal loss, distance, signal or noise, how much noise is in the area, microwave ovens, and that's always one of the not always, but frequently one of the problems that they give you is we have a wireless access point in the break room and people can't get anywhere during lunch. What's the problem? Well, they're all using the microwave, and it's interfering with things there. This is a picture here of Insider, the INSSIDER, and you see that it shows you where you're going across the channel, and some of these you can see channel bonding going on of the systems, and gives a good look at what goes on, what an indication of the signal strength, and it will, as long as you have the capability, do both the 2.4 and the 5 gig. It gives you the data rates that you have over here. It's a pretty handy little device, little system that we can do that with. The signal to noise ratio, Wi-Fi analyzer, signal loss, Wi-Fi analyzer to find out what kind of signal we have. Wrong antenna type can cause us issues, antenna mismatches when we do these things. Device and bandwidth channel separation, that means that we have too many devices connected to an access point, or too many devices trying to use that particular channel. Multiple devices all on channel 1, probably not going to work out. I try to get mine away from everybody else, at least the strong ones. All the channels are in use around here. What I've got to do is go to a channel where the other one that's in use has the lowest signal. The other issue could be firmware or untested updates when we put something on, and it makes things work so much better all the time. If you can, you need to test updates in a lab environment. I know that's not always possible, but if you can do it, that's what you can do. Overlapping channels, we talked about bounce. If you have mirrors or stainless, things like that, it can bounce off of those. Electromagnetic interference, EMI, can affect the signal, obviously, when we go through these things. Environmental factors, concrete walls, we've talked about. Window films, some window films can do that. Sometimes you want the window film to keep the signal in. Metal studs can affect it. It can disturb the signal, send it out in all different directions. Jamming and rogue access points. Jamming, everybody knows what the frequencies are, so we can do that. The rogue access point, we're going to put one in there. A wireless device will connect to whichever access point has the strongest signal. That's the one it's going to try to go to. So our rogue access point, try to get people in, maybe to watch the traffic, maybe just to create our own little network. But the problem is, once you get those in there, you've just bypassed your firewall, and it makes it available to somebody that may not have good intentions. Wrong SSID and authentications issue on open networks. Wrong SSID, somebody tries to connect to the wrong SSID and they can't get authenticated to it, can't figure out why. You can have multiple access points with the same SSID. It's not a good idea, but you can do it. But that could really confuse people also. And then we have standards mismatch, the wrong encryption, throughput compatibility, the frequency bands incompatibility, channel usage and MIMO configuration, channel usage, all of these things, wrong encryption. If we have mismatched standards, just like mismatched anything, it's not going to work for us. So with that, the 802.11 standards we looked at, ad hoc and infrastructure and mesh topologies. Hopefully they make some sense. Ad hoc or computer to computer infrastructure, we're going to have an access point, and then mesh topologies. The advantage to the mesh is they actually set themselves up. They establish their own connectivity, and they'll determine the best path also. Perform a site survey and understand issues impacting site design. That's mostly going to be too many of them in the same location, or too many people trying to get onto the same access point. And then troubleshoot wireless connectivity issues. And I guess that we can try these questions here. What mechanism does RTS CTS support? RTS is request to send and CTS clear to send.
CSMA.
CSMA. CSMA CA.
CA. Collision avoidance.
CSMA CA, yeah.
Collision avoidance. Which IEEE standard specified data transfer rate of 54 megabits per second?
It's the 802.11G.
G and?
G
And A, right? Because A was originally 54 meg. What options may be available for 802.11n network that are not supported under 802.11g?
5 megahertz.
5 megahertz, yep.
I would have to guess.
It has both. It has 2.4 and 5.
Backwards compatible.
Backwards compatible. What about the bandwidth that we can create with it? Putting channels together, can we do that?
On the end?
Yeah, yeah, on the end, yeah.
30, 80 or something like that. 160.
Yeah, you can do channel bonding, and then it was the first one that had MIMO, multiple input, multiple output. True or false? Stations with 802.11ac capable adapters should be assigned to the 5 gigahertz frequency band.
I would say true. It only is 5 gigahertz.
It's designed to work at 5 gig, yeah. What is a BSS ID? And that's basic service set identifier if you really want to know what it stands for.
Data.
Say what?
It has lots of data.
Has lots of data. What is it? But what is the BSS ID?
The security?
Nah,
No.
we're making this way too hard.
Yeah.
Way too hard. BSS ID is trying to get to it. Here we go. The BSS ID, the what?
MAC address.
The MAC address is the BSS ID. And that's all. That's one of the multitude of things that's going to be in that beacon frame that they send. You can change the data. You can change the rate it sends, but it's going to have to send it. What are the advantages of deploying a wireless mesh topology over an ad hoc one?
Connect directly to the access point. The ad hoc connects to the other wireless.
Yeah, the ad hoc just is a machine to machine, but the mesh does a lot of stuff, doesn't it?
Overlaps.
It overlaps. It sets itself up, does its own configuration, does its own route discoveries, does its own peer arrangements, and it finds the best path, does path discovery. What type of access point is designed to work with a wireless controller? Here we go. Which one works with a wireless controller? It's on the slide.
Well,
Lightweight access point, you're saying?
Lightweight access point, yeah. The controller sends all the configuration. The controller actually manages the lightweight access points. You can't manage them yourselves once you upgrade it to a lightweight access point. True or false? Suppressing transmission of the WLAN beacon improves security.
I don't know that.
Huh?
With the beacon, was the beacon, but the beacon was good.
Yeah, you can't make the beacon go away. You can change its rate, but you have to have it.
Let's turn SSID.
Well, it does more than that. It sends all of the information. It sends the information about the system. I've got a packet somewhere. I'll see if I can find it tomorrow and show you what all is in that beacon frame. It's one that I did when I was doing a wireless class. Captured a beacon frame using a Linux machine, and it is huge. What constraints should you consider when planning the placement of an access point?
All the above.
All the above, yeah. Like what? Give me a couple.
Walls, microwave.
The last one, true or false?
The last one was false. You can't. Your beacon cannot be suppressed completely. It has to be there. You can't make the beacon go away. So, what constraints when you plan the access point? You said all the above whiches?
Walls and metal studs.
All those things, yeah, walls and,
Microwaves,
range, interference, obstructions, number of clients, device density, access. Yeah. What is beam forming?
No idea.
Beam forming was where we were able to send a stronger signal in one direction in the MIMO. Which frequency band is less likely to suffer from co-channel interference?
$5,000, I guess.
About that one there, the 5 gig. See how it has distinctive channels, unlike the B, which has overlapping channels. Or the B, the 2.4, the B and the G.
So the answer was what?
Huh?
The answer was
Is the 5 gig.
5 gig, yeah.
See this image here, see how clean the channels are on the 5?
Mm-hmm.
And see how sloppy they are on the 2.4?
Oh, yeah.
So we have overlap for everything. We only have 3 distinct channels, and all of the channels in the 5 are distinct. What is a heat map?
A heat map is the one that allows you to do the site server.
Mm-hmm. You map where everything is, what kind of signal strengths you have, and that's what you're going to do in a site survey is what's going on with our wireless, right? Okay, well, I got a couple more. Widget Corporation has provided wireless access for its employees using several access points located in different parts of the building. Employees connect to the network using 802.11g compatible network cards. On Thursday afternoon, several users report that they cannot log on to the network. What troubleshooting step would you take first? What would you do first?
Can you check the terminal?
That's right. Check to see if they're all trying to get on the same one. Have you got a network problem, or you got an individual equipment problem? One more. And their answer was check whether the problem machines are trying to utilize the same access point.
We got too many on one access point.
Yeah, it could be, or it could be that you have a bad access point. Your office block is hosting a conference event. During the morning coffee break, several guests report that they cannot access their webmail. What is the likely cause? Try the one that you said earlier, Tom.
What was the microwave you're saying?
Well, no, not the microwave, but how many people are now in the building trying to use
overloading? Yeah,
overloading.
Checking their email all at one time.
Yep, yep,
Too many users.
yep. Device saturation. The access point is likely to be experiencing greater load than usual and cannot cope with the volume of requests. And remember, this is all has to be it's collision avoidance, so you have to have permission, request to send and the clear to send every time, and then each packet has to be acknowledged, although in the end we allowed multiple packets to be acknowledged at the same time. Questions? The next topic for a few minutes is WAN technologies. We talked about LAN, Ethernet predominantly on the local area network. There are lots of WAN technologies that are available. This will be an overview of some of them. And the real differences between LAN and WANs, I know we always say that a WAN's big area and LAN's small area. WANs do connect networks together, but it's what layer 2 protocol they use, how they're configured there. It's going to be one of the primary differences, because once you get to IP, the IP, whether you use IPv4 or IPv6, is the same whether we're using a LAN or a WAN. So you want to understand the provisions of telecoms, networks, and the internet, identify technologies and protocols used to implement WANs and wireless WANs, describe and differentiate types of local access network. So wide area networks, public networks, enterprise WAN, we have circuit switched and packet switched networks. And the difference is obviously how the switching takes place. In a circuit switch network, we create a circuit to the destination, and it could go any of these ways, and generally these things will find the best path. We create a circuit before we start sending the data. In a packet switch, the first packet may go this way, the second packet may go this way, and the third packet may go this way, and that'll be based upon whatever the best data path is. And as you can see, the different paths, these things may get it here out of order, and that's where the numbering system comes in to put them back together in the correct order, so we'd have 1, 2, 3 instead of 1, 3, 2. There's no guarantee that they're going to get there in the proper order. Packet switched, connectionless, and we have connection oriented. Connection oriented here can be connectionless. It sends them in the best path. In the WAN topologies, we can have point-to-point, mesh, hub and spoke. A hub and spoke, and both of these are a hub and spoke of sorts anyway. We have a centralized router, the hub, and then the spokes that go out on it. A mesh, you remember, everything's connected to everything else, and that becomes a really big issue, although there are some technologies that actually allow you to buy a mesh without having to go out and spend an excessive amount of money. It's not going to be inexpensive, but you can actually buy one, and then point-to-point is one machine to the other. And the protocol that we're going to use in a lot of these cases is going to be the point-to-point protocol, PPP. Telecommunications networks, this shows a CPE, customer premises equipment. Let's go to CPE. The local loop, sometimes called the last mile, lease line, and the local exchange for the system. Sonnet's going to be a high-speed telephone system, MPLS, ATM, frame relay. Different topologies in the cloud here, and the fiber optic trunks, and then the core or backbone to get the information from one location to the other. This is the internet. we have internet access for these things. Let's see. The internet exchange, I'm going to get this, see if I can get this map over here. There are certain points in the world where the ISPs can get onto the internet. And this is a map of those. I guess the U.S. would be the ones that we would be predominantly interested in. And for the East Coast, there's a whole bunch concentrated in Washington. Then we have Atlanta, Jacksonville, Missouri. Denver, and you guys in Denver may know where this is. It gives us the address 910 15th Street, Denver. So that is a place that we can get, that the ISPs can get onto the internet. Atlanta, Cox Cable is a big player in the Atlanta area. So only certain points that they can get onto the internet. And that's what we're showing here in this thing, that the internet exchange point, the IXP, and that's what that map was, allows them to actually access the cloud itself. We have ISPs and IXP when we go through these systems, and we are the subscriber, so it is a hierarchical system. The PDHT carrier, these were the originals, and they say that there's the first generation of digital signaling implemented. It was developed by Bell Laboratories, and the plesiochronous digital, I don't know if that's the right way to say it or not, hierarchy allowed more than one signal to go onto a carrier. It was a time division multiplexing system. And what it had was DS0s. DS0s are 64K systems, and they're narrowband, and it put several of them together. DS0 is a narrowband circuit, 64K. DS1 or T1 wideband, you put, I think it's 24 64Ks together, and you get a T1. A T1 is 1.544 meg. That's another one of those numbers that sometimes they want you to know. E1 is the European standard, and it is 2.048. It puts more of them together. And then the T3s and the E3s, we go up in speed. E1, the CEPT0, how fast do these things go in the bandwidth? And as you can see, when we get up to E3, C3, we're in the relatively high bandwidth. 512 channels to get here when we do these things. We have 24 for the US. The US, the DS1, that's the US standard. The E3 or the E1, CEPT or E1 is a European standard. It uses 32 64K channels in order to get that bandwidth. The SDH or the SONET, the synchronous digital hierarchy, and the synchronous optical network, SONET, typically going to be a voice network, and we get even higher speeds here. OC3 and OC12, if we go over here, OC3 is 155 meg, OC12 622, until we get to OC7 68, you get 39 gig for those. It can be a mesh or a ring topology, and if it's a ring, it's probably going to be a counter-rotating ring for reliability. If one ring goes down, the other one picks up the load. You can add or drop multiplexers in order to put multiple conversations. That's what the multiplexer is going to do, is put multiple conversations on the system. WDM, wave division multiplexing. We have coarse wave division and dense wave division. The coarse wave division is shorter ranges for the metropolitan area. Dense is for longer distances. So the coarse uses up to 16 one-way or 8 bidirectional channels, and the dense uses more channels, and it can support over 100 channels, and it's going to be best for the long range. Ethernet over SONET, 10 gig WAN, and the PHY is a physical layer, is a physical definition. 10 gig base, and base is baseband, if you remember. SWLW and NEW is going to give us the ranges over here of what we use. The Metro Ethernet is what we normally call a MAN, and it's going to be within a metropolitan area typically when we do these things, and wave division multiplexing is what we've got here. What that means is we do fiber, we have the different colors that we can put multiple signals on this thing with the multiplexing, and go across a single strand and then demultiplex them. And this one, it says it's got 40 virtual high-speed channels per physical fiber, expanding the capacity of the OC48 ring from 2.5 to 100 gigabits per second. So all of these things designed to give us more and more and more bandwidth. The frame relay goes back someday, and it's been popular for years. It's a packet switched network, and this is the one, and this is just a simple version, uses DELSI link, the digital link connection identifiers called a DELSI. And what you create in the cloud are, this is going to have frame switches in it, and this just shows going from one to the other, but there may be multiple switches in here that it goes from one switch to the other to get from point A to point B, and then a different path to get from point A to someplace else. So we can buy this frame relay connectivity and actually probably create a mesh with it without going bankrupt. They're connection-oriented circuits, has congestion control and quality, QoS, quality of service control on these things. The protocols on the routers are the things that are going to have congestion control. Routers will actually, the packets will actually check the data, the congestion, as they go from point A to point B, and when they get there, they'll tell the router that's receiving the packet that whether there was congestion or wasn't congestion en route. This is a picture of the asynchronous transfer mode, and usually asynchronous transfer mode is what is used in frame relay. It's a fixed cell, and what this is showing is a fixed cell switched packet, and the difference between it, one of the differences, a big difference between it and Ethernet is Ethernet didn't have a fixed size, whereas ATM, asynchronous transfer, does. And traffic shaping here, what it's showing is, in the traffic shaping, is the 3 system here gets more than, we get one cell for the 2 and 1 cell for the 1 and multiples for the 3. So that's the traffic shaping. It sends the traffic that should go out first, the quality of service, the traffic should go out first, and then saves the others to be sent when it gets the chance to do it, when the opportunity is there to do those. Multi-protocol label switching, it says it's a traffic integrator. It's a packet switch network, uses packet tagging, and we have routers here. We have CPE, we have edge routers, and then here we have the label routers. What happens is when data gets here, a label gets put on it, and once the label gets put on it, the path is selected and when it gets to go, because it uses a quality of service also. So the label switch path for the packet through the cloud, the label edge routers, I know these are lots and lots of terms, but the edge routers put the label on it, and then the switch path, the label switch path through the label switched routers gets selected so that it gets from one to the other based on whatever the best path is that it can go through the system. Local loop services, we have dial-up and 33 kbits per second, 56K down with some ISPs, but dial-up probably going to wind up being our emergency sort of system if everything else fails based on the speeds that we have today with everything else. Digital leased, and you can lease these from carriers, dedicated lines, TE and fractional. A fractional is we would buy part of a T1, T2, T3, a T1 1.544, a fractional T1 we might have 5 or 6 or 7 or 800 meg instead of the instead of the full 1.544 meg. ISDN, we have BRIs and PRIs. The BRI is 128K and it is a digital system. And it has the 116K. The 16K is actually the control channel. It's called the data channel, but it's the control channel. The BRI is where the data actually goes. 128 bits. If we have a PRI, we have enough of the 64K channels, whether it was 24, to get a T1 or an E1 equivalent of these things. And the publicly switched, the PSTN or the POTS, the plain old telephone system, dial-up access. We have the router going to dial-up access to the PSTN to go from modem to modem. And these are true modems, unlike, well, cable modem is too, because we're going from binary to digital. DSL, digital subscriber link, is a broadband that is available in some areas where cable isn't. I don't know that it's as popular as cable modem. Symmetrical DSL, and symmetrical means that we have the same upload and download data rates. So cable modem is typically going to be, or at least mine is asymmetric. Asymmetrical DSL is when we have uplink, what this says, uplink for 1 meg, while a downlink can be up to 24 meg. So asymmetric means that our downlink is going to be much higher than our uplink. And that kind of makes sense because typically you're going to be getting stuff and not sending stuff. If you're sending data, then you need, and in a business, if you have a website or something like that, you need symmetrical connectivity. Broadband cable, HFC, hybrid fiber coax. The hybrid fiber coax has got coax and fiber in the same container. And fiber to premises, I don't know if any of you got it. I certainly don't, and I wish I did, but that's becoming more and more and more popular as we actually get fiber going to our homes. Broadband cable, let's see, cellular radio, and this is 2G, I think we're 3G, 4G now. The global system mobile communication uses code division multiplexing. They are circuit switched data. The packet radio 2.5 gig, 3.5 gig, 3 gig, and 4 gig. WiMAX is a longer range, higher speed wireless. It says fixed and mobile deployments. It can be mobile. It can be on an antenna. The WiMAX 2 up to 4 gig and up to a gigabit for the fixed sites. General packet radio services, more ranges, and the 3GPP, universal long-term, LTE, long-term evolution, LTE, that's what the cell phones are. And it says advanced for 4G. The 3G kind of emulates some of the 4G capability. And then we have microwave satellites. The problem with satellite is one that you get if you can't get anything else, I think. Problem with satellite is it's going to have some pretty significant delay. Originally, satellites, you had the up was a telephone link and the down was from the satellite. and now most of them are up and down from the satellite, but they're way out in space, so you're going to have a pretty significant delay when you use those things. I know that was a drink with a fire hose, but the WAN technologies are there. The overview is what's expected, I think, of those. When most of us are working on networks, we're going to be working on local area networks. We may be working on a wide area network, but that's generally something that you progress to. But let's see if we can do any of these questions anyway. What's the main advantage of a circuit switched networks?
It creates circuits before sending data.
Yeah, so it's guaranteed, and it's a guaranteed connectivity, and it's going to be a guaranteed bandwidth, level of bandwidth as it goes from location to location. What's an internet exchange point? That was that map I showed you. What does it give you?
Access to the internet.
Access to the internet. It's where the ISPs get on the internet. What bandwidth are T1 and E1 links? And why are they different?
I know T1 is PRI.
Yeah, but T1 is what speed? I don't know that.
1.544 and 2048.
Yeah.
The number of 64-bit channels.
Yeah, because the T1 uses, and here it is, the T1 uses 24 channels and the E1 uses 32 channels. The E1 is the European standard and the T1 is the US standard for T carriers. What 10 gigabit Ethernet and SONET standards are interoperable? I think that's buried in the book somewhere, but it's the 10 gig WAN PHY is interoperable with the OC192. Between you and me, I don't know. You can do the question banks and see what they say, but I think that some of these things, I don't know that I would memorize a whole lot of the OC and the 10 gig WANs and those sorts of things. What distinguishes ATM from Ethernet?
Size of the packets and quality of service.
Size of the packets and quality of service. The ATM is a fixed size, and Ethernet can be a variable size. What is the difference between IP and MPLS routing?
MPLS has to do with labeling.
Does labeling, and it's got a quality of service in it. Here we go. Doesn't say that on here, but you have quality of service. It labels the packets based on the quality of service, and IP routing is best effort. It is the best effort. It just has a path, and all of them compete at the same. There's no labeling, no quality of service in general IP routing. What is the upper limit of a dial-up modem's connection speed?
DSL.
What's the speed? There we go. Dial-up. 56K. And what they say is 56K for the downlink and 33K for the uplink. A 48K uplink is possible with V.92, but only by reducing the downlink rate.
Take that.
And hopefully, well, none of you still have it because you couldn't be on this connection with a dial-up. What place does VDSL have in terms of access to public networks let's see. very high bit rate DSL.
We skipped that line, I remember.
Oh, I did, didn't I? I didn't mean to.
We did skip that line.
High data rates over limited distances, so that it's 100 megabits, but it's only going to be 100 meters. In this respect, it supports fiber to the curb, providing the final link from the fiber distribution frame to the customer premise.
FDDI went away.
Say again?
FDDI went away.
Yeah. Yes, it did. It's been gone for a long time, but the concept, I mean, there's still some systems. FDDI is fiber data distributed internet, maybe. It's the counter-rotating interface, yeah, but it's the counter-rotating ring, and there's still a counter-rotating rings. The concept's there, but I don't think it uses the FDDI, that protocol. What standard? Yeah, it used to be, not anymore. What standards are intended to support true 4G wireless? It's what's in all the ads.
LTE.
LTE, long-term evolution. Assuming that sufficient bandwidth can be provided, what factor limits the usefulness of microwave satellite internet link?
Ultimate latency.
What's the problem with satellite other than it's slow?
What?
The delay that you have.
The delay, exactly. Takes a long time to get there and back. We used to have connected. Antro, what are you doing, man?
I'm not doing anything. This computer's acting crazy.
I guess it is. Sorry. We used to have DirecTV and a cable connection to watch the football games, and I could watch the kickoff on the cable, and then flip it over to the satellite and watch it again. That gives you an idea of how slow it is. But there is a lot of delay in the satellite. So let's see. Let's take a break. Let's come back at about 5 after. Yeah, about 5 after the hour.
Yeah.
So for the last topic tonight, what we want to look at is installing remote access links. Remote access, big deal today because people working at home, people traveling, trying to get back and connect to the corporate network. And the remote access that we have, we want to be secure so that we're not giving away stuff on the internet. And this one is about setting up those. There's to identify the components and security considerations of different remote access and VPN technologies. And a lot of it is about the virtual private networks. Identify the features and vulnerabilities of remote connection protocols, including point-to-point tunneling protocol, layer 2 tunneling protocol, IPsec, SSL, TLS. SSL is one of the ones that a number of people are going to now because typically the port 443 will be open through the firewall to get to the web server, the secure web server, so you just use HTTPS in order to go not have to open up additional ports on the firewall. Install and configure dial-up dial-up and broadband modems, multifunction network devices, and components for WAN links. So remote access, we have remote access services. We're going to probably have a server at the other end that allows us to connect to it. You can control who gets on to the system remotely by controlling who gets dial-up access. When we get to VPNs, at least in Windows, the VPN is a dial-up service. So in order to allow somebody to connect with the network via a Windows server, you're going to have to give them dial-up access. Point-to-point protocol is the layer 2 protocol that's typically used with this thing, point-to-point tunneling protocol. But we have layer 2, and it encapsulates the IP protocols, and that's what we did all the way down. Is we had the headers, but we're going to do that. Multi-link point-to-point protocol. Multi-link allows us to put multiple modems together to have a higher speed dial-up. Point-to-point protocol over Ethernet is something that can be used in asynchronous transfer mode, and it can be used so that the ISPs can better bill the client, keep track of what's going on. Tunneling and encapsulation. Tunneling, we always draw these really cool tunnels. What tunneling really is we encrypt the packet and then add a routable IP address to it, send it across the internet. Can it be intercepted? Yes. Can it eventually be cracked? Yes. The objective of the encapsulation is so it takes so long, by the time somebody gets it done, it's not a whole lot use to them anymore. But this thing here is showing just simply a system dialing in, computer A, computer running TCP, and it goes over a PPP connection, and modems are, dial-up modems are PPP connections, and dials into a remote access server. It would then get an IP address that's on this network back here and be able to connect directly with these machines, and that's the objective of doing that. The remote access server is kind of the gatekeeper for these things. When we start doing VPNs, the firewalls frequently can be the point that we connect the VPN to. That way you don't have to go buy licenses and have a server sitting out exposed either on the internet or in the DMZ. The VPN, the types that we have are site-to-site, host-to-site, and host-to-host. What does that mean? Site-to-site VPN, we got one here, a picture here. We got a VPN router, goes across. See, we have this nice little pipe across the internet. How many routers do you think are in that nice little pipe there if we go from point A to point B? So what we do is encrypt the data stream and encrypt the whole thing, actually, including the private IP. And then we add an IP header to it so that it can be routable, because the routers en route are not going to be able to read the encrypted addressing. But site to site, we connect entire networks together through a VPN, virtual private network encryption. Host to site, a VPN connect, and this one we would just go from a single computer. Somebody working at home maybe connects to the site and gets access to all of the resources on the network. You need to be really careful about this, because how are you going to be sure that that user is maintaining the antivirus and the anti-malware, and it doesn't have viruses, it doesn't have malwares, and all that other stuff. One of the companies that I work for did hire somebody to work remotely from home to do some work, and I don't remember what it was. But when they finally checked the machine, they found I had somewhere around 30 or 40 viruses. So you have to be careful of those. Host to host, this goes from computer to computer, and we can do VPNs from one to the other. If you're going to do it at home, what you've got to do is do a port forwarding on your router so that it forwards whatever that port number is, and for a point-to-point tunneling protocol 1723, forwards that one to whatever machine you have the information on. So if we had our router and we wanted to have a web server, we would forward port 80 to the computer that's running the web server when we do those things. Point-to-point tunneling protocol and layer 2 tunneling protocol are two of the popular ones. And what we have here is the PPP header, the tunneled point-to-point protocol frame. The PPP header, we have IP, TCP, and the data, and this is, it says MPPE encrypted. This is the encrypted data. We also have the GRE header, and remember GRE is for the general routing protocol, and then the new IP header that's added to it so that it can go across the internet. Once it gets to the other end, all of this stuff is going to be stripped out. But you do have to configure your firewall to allow the IP in along with the GRE header and port 1723 for the control link. So 1723 for point-to-point tunneling protocol, the port number, and the protocols that we have to allow the encapsulated in IP GRE header. So point-to-point tunneling protocol runs over PPP, point-to-point protocol, supports TCP IP and the general routing encryption protocol, couldn't remember what the E stood for, and uses Microsoft encryption, but the link establishment process has some vulnerabilities. You may not, when you're establishing the link establishment is not secure, so somebody could possibly intercept some specifics, maybe usernames. Passwords we'd hope would be encrypted as it goes across there. Layer 2 tunneling protocol is combined with IPsec, and IPsec is IP security. Secure socket layer, SSL, and transport layer security are becoming more and more popular because we don't have to do as many firewall changes. And we can publish HTTPS applications that we allow access with. And HTTPS, the S always is going to tell us that we're going to be secure. OpenVPN is an open source VPN software. And when you're talking open source, typically you're going to run it on Linux, although it may be some of those things are ported over to Windows. Windows already has its VPN capability, so you may or may not need it. uses SSL to authenticate and encrypt the tunnel. Can work over UDP by establishing the control channel to mitigate for UDP's connectionless, unreliable data transfer. And I think we talked about that if we did that, the control channel is the thing that's going to tell you if there's something wrong. UDP, the protocol itself won't, but the reliability is done with the control here in the VPN server itself. It multiplexes the network traffic over a single secured port, which is kind of handy because sometimes in Windows we have to have multiples, the 17, and there's a 1540, I think, that also has to be open sometimes. Can work in bridged mode to tunnel Ethernet frames or router mode to tunnel IP packets. And the secure socket SSTP uses machine certificates to protect authentication and session setup. Remember, certificates are the things that have to be signed by the certificate authority, and they can be used to generate encryption schemes, keys that we do these things with. IP security. Say again.
What was UDP? What does that mean?
Oh, UDP. Why won't it come to me? Anyway, it's the connectionless protocol. TCP was connection-oriented. UDP was connectionless. It was the much smaller packet.
Okay.
And why won't the U come to me? Help me out, somebody.
I think that feels sweet. And trail?
I'll get it here. It'll come to me.
Why are you calling me out?
Whatever. Anyway, you don't want to know it. Okay. What does UDP mean?
User Datagram Protocol.
Okay.
It's the connectionless, and some people call it the unreliable protocol, but it's connectionless.
I was talking on mute. I got the datagram protocol and I said unreliable, but I knew that was wrong.
User Datagram Protocol. So IPsec, the IPsec, we have the payload here. Authenticating headers, there are two things we can use. We can use an authenticating header, and this is used to authenticate the computers to each other. Sometimes that's as important as anything else. If you have data, if you only are worried about that you're connected to the right location, then the authenticating header may be the only thing that you need. And this is authenticated header, and this is called transport mode in the IPsec datagram. Whether the payload, TCP, or UDP, whichever we have, and then the IP header, the authenticating header ensures that we're connected to the correct location. Authentication and integrity only. And integrity means that we sign it, and when we sign it, we get a hash, and at the other end, it's got the hash, and it hashes the packet at the other end and compares the two hashes to be sure that it hasn't changed in route. The encapsulating security payload encrypts, it's called, and this is IPsec datagram with transport mode, encrypts TCP, UDP, and the payload itself. It does not encrypt the original IP header. So that means that we're probably going to be able to NAT this thing. So it encrypts the payload, but not everything else. Let's see, IPsec datagram. The IP header is unencrypted, used for end-to-end communication over the same network. And the reason you do that is you over the same network, over the internal network. This is over the unencrypted over the same network. We don't need to encrypt the header to do that. And this can be a client to server. You may need to use encryption over your local network. You may not. Depends on how secure you need stuff to be and how curious people are. Tunnel mode encapsulates the encrypted packet within an encrypted header. So in this one we have our original IP header and everything else, and this all becomes encrypted. And we have the encapsulating security payload. We'll put a new IP header, an unencrypted header, so that it can get through the routers. Used when traffic's got to pass over an intermediate network or a VPN, gateway to gateway, server to gateway, or server to server, depending on how the connection's made. It may go from, and gateway to gateway would be like network to network. We would have firewall to firewall encryption on this thing. So we would have two public IP endpoints that would communicate with the unencrypted IP header. And as many times as we draw this nice little tunnel, there's going to be multiple routers in here, and that's why you have to have the unencrypted header. Server to gateway, it may go from a computer to a firewall to a gateway to an endpoint, or it may go from computer to computer, server to server. In that case, it's got to go through the firewall. We'll have to do the firewall configuration to do that. The Internet Key Exchange, IKE, is the way that we exchange encryption keys in order to make the encryption and the authentication work correctly. Remember, authentication header, we can use the original IP address, the ESP, we can't. Dial up, and this is what Microsoft would look like for the multi-link, which is when we would have more than one modem, this is multi-link connections, more than one modem put together to form a single connection to give higher speed for these things. LCP, link control protocol extensions are there, and software compression so that it compresses the data in the software compression. Can configure user rights. You can configure the system so that only certain users can use dial-up. You can do callback to be sure that you're getting the right user. You would have to have phone numbers on file. Then the user dials in, hangs up, and then you call them back. That also was a way to allow the company to pay the phone bill instead of the user to do that. Dial-up, we can have authentication and encryption with it. VPN, remote access server, in a Windows environment, it's really not a very difficult configuration. You just go in and add the protocol, add the VPN server to it, and then you go into the dial-up properties of that user and authorize them to dial in, because the user right or user permission here by default is no. So you have to authorize users either by policy or individually to be able to connect to these things. And once you get that done, said the setup's relatively simple. If you're on the back side of the firewall, you're going to have to allow the ports through the firewall in order to get to the VPN server to do the connection, and it'll give the user at the other end an IP address that's on the network, that's routable on the network, to be able to do those things. VPN concentrators are a device. If we have multiple VPNs, one of the places I worked I think we had 12 sites, and everything came to the headquarters even to go to the internet, and all the traffic was secure. So instead of trying to configure a router with all these 12 VPNs, we had a VPN concentrator that they all connected to. So it allows multiple VPN connections there, and then we can manage it much more efficiently through the VPN concentrator instead of trying to load down a router. You can establish VPN connections to a router, but it's much better if you have several of them to have the concentrator. It talks about installing the remote access links. We've used the term the access provider network. We use the term DMARC for several times. Demarcation is where the data comes into your premises, and inside of it we have customer premises equipment. A DMARC extension is if they bring, and you move stuff around maybe, but if the DMARC is at an inconvenient place to connect to your network, it can be extended, and it's called a minimum point of entry, and a DMARC extension allows that to happen. Leased lines, a channel service unit, TSU, DSU, normally a WAN interface, and this is it says it's a card, it's a module that goes into the router, has an RJ45 connector. Typically the CSU, channel service unit, data service unit, is the device that prepares the signal for transmission on the T1 line. The Smart Jack terminates typically the T1 line, and say it's got a loopback component that allows the ISP to check the line. So if you have a problem, they can actually check the line. And then we have the line drivers and repeaters. We've talked about repeaters, and the line drivers are going to be the drivers for the lines themselves. Modems, analog modem, hopefully you're not going to have to do that, but we'll connect it, and this is an external modem for, I think, not a whole lot of internal modems anymore. The internal or external USB or serial device, the analog modem, the RJ11 port, RJ11 port over here that can connect it to the phone system, and then the serial port that's going to connect it to the computer, on-off switch, and the power, obviously. An ISDN adapter, I've always thought that ISDN had so many different things so that they could have a whole bunch of test questions on it, but the terminal adapter is what is on the system itself, and the terminal adapter connects to the network terminator, which then will gives to the terminal equipment that's going to get us on to the network. A DSL modem, very similar to a cable modem. These two are here on the same page. A multifunction DSL router. Sometimes they're put together as are cable modems. A lot of cable modems now are combined with the router so that you just have one device on your network. RJ11 phone line. It also has, and they'll provide you filters to go on all your phones because these are different frequencies, and the DSL signal is kind of a squeal, which wouldn't sound very pleasant on the telephone itself. The cable modem, we bring our cable connector in, and then RJ45 to the router, or if it is a combination device, it'll have the wireless and the switch built into it. Ethernet or USB to the PC. Sometimes to the PC. I think most of us are probably going to routers instead of directly to a computer. If you've never experienced it and you want to change your router sometimes, what happens is these MAC addresses get kind of set into the cable modem, and those are the ones that it is used to having, and you won't get connectivity. To get it bled down, you may have to turn your cable modem off for, I don't know, five minutes or so, and then you can put it back on. It'll do the whole startup, and we'll find your new device. WAN issues, loss of internet connectivity, and that's probably going to be the first thing that you're going to hear. Not that I can't get to the server to do my work, but the internet's down. And that can be a multitude of problems, and we talked about some of the tools we can do, a ping, a trace route, and those things to see what's happening, see where the connectivity is failing. The devices and cabling could be a problem. Something could be turned off. The power, I told you about the instructor that taught the whole night with and this was back in the day of hubs, with the hub turned off and couldn't figure out why none of his computers could connect. The connectors could be improperly made, improperly connected together. They may be mismatched connectors, could be damaged. You need to check the LEDs, and the LEDs can be really handy, and they're frequently called link lights. Are the lights working? Is there flashing? Is the flashing really strange? If you have regular flashing, it's usually not a good sign. If you have a switch and they're all flashing simultaneously, that's usually not a good sign also. You can do link tests on these things. Another issue could be configuration, and they always talk about that, and I guess configurations could get changed, but it seems to me that once you get the configuration on these kinds of devices, you're not going to change it very often. And if you do, you'll probably know immediately. That happened one time to a friend of mine who was a network administrator. He was trying to stop an individual user from using the internet, and he did that, and then he stopped everybody else, because what he had forgotten was at the end of every access control list in a router is a deny all that won't let anything out. So you had to permit everybody else after you denied the one individual. Routing could be an issue, and that's where ping and trace route come in. Name resolution, is DNS working properly? Is it properly registered in DNS if we're trying to get to machines that we are that we're own the zones for, or that are they properly resolving? And that's where you can use Nmap in order to do that. Firewalls and security. Are you able to get through the firewall? Do you just get to the firewall? Is the firewall denying access to the packets coming in? Interface errors. Those are frequently going to be shown up with lots of activity on the link lights, and what caused the error. Then you got to troubleshoot what caused the error. Is there interference on the system? And then satellite issues, latency, the amount of time it takes to get from one location to the other. Customer premises equipment are on the IRIS side of the DMARC. The loopback on this, I think, is when you can test the line with a loopback connection, that the ISP can do that. Are the router configurations correct? And have you changed it? Has anybody changed it? Has anybody restarted the router? Because if you made some changes and then didn't save the changes and restart the router, the changes are no more. Because when you make changes on a router, they go into memory, and you have to manually save all of them before they actually take effect. So when you reboot the next time, if you haven't saved them, the configurations are no longer there. DNS and DNS split horizon. The DNS split horizon is when you list both your internal and external addresses using the same domain name. You have to be really careful about that, because you don't want your internal addresses resolving on the internet, and you have to be sure that your externals are actually resolving. A good way around that is just to have two domains. You might have one as a .com and one as a .net. Last place I worked, we had a .edu and a .net. Some of the and the internal and the external domains were different. It made it easier to keep track of what was going on with those things. Security policies, internals or ISP policies, can affect what's going on, and then fair use, throttling and blocking from the ISP. What are they going to do? How are they going to control our data? So the reviews, the components and the security considerations for the VPN technologies, the features and vulnerabilities of remote connection protocols, including PPTP Layer 2, point-to-point tunneling protocol, Layer 2 tunneling protocol, IPsec, and I think one of the keys about what layer does IPsec work at is the IP part of it. SSL and TLS. Installing configured dial-up and broadband modems, multifunction networks and devices. And I think the big thing about the broadband modem is you've got to get the MAC address listed with the ISP. So let's do these questions and then we can be done for the night. What are the three main topologies for implementing a VPN? What are the topologies?
Site to site,
Yep.
host to site, and host
Bang, point to point.
Yep.
Mesh.
wrong.
What ports and protocols, yeah, she's right, and I'll say it again what she said, host to host, site to site, and host to site. What ports and protocols must a firewall allow to support point-to-point tunneling protocol connections? I don't know if that port numbers on any of these slides. Anybody remember the port number?
1723 is the one I remember.
1723, and what was the protocol that you have to allow? That's in here, isn't it? What protocol?
UDP.
UDP. UDP. It is UDP, but it's the GRE protocol. And I was trying. It's on one of those slides, but there it is. It's on this slide right here. The IP header and the GRE. And then port 70. Huh?
Well, it's reading that now. GRE?
GRE.
Routing and encapsulation.
General Routing Encapsulation Protocol. How does SSTP improve the security of a VPN connection compared to PPTP? There it is, I think. Let's say that gives a hint anyway. I thought one of the slides actually said it. There it is, yeah. There it is. What does it say down here at the bottom? Secure SSTP. What does it use?
Certificate protection?
Certificate protection, yeah. A point-to-point tunneling protocol doesn't. You can have, it generates its own encryption and then you have to do the log on itself. But this one actually uses the certificates to protect it. So the answer is Secure Sockets Tunneling Protocol, SSTP, uses a digital certificate and the SSL TLS on the VPN gateway to encrypt the setup of the VPN session so that we're not revealing usernames and IP addresses and connection information as it goes through across the internet. What IPsec mode would you use for confidentiality in a private network?
VPN?
Yeah, VPN is what mode? What mode of a VPN? Take a look at your screen.
Oh, IPsec?
IPsec would be part of it, but if we have the same network, you can use transport mode here instead of tunnel mode because we don't need to encrypt the IP header. If we send it out over the internet, we're going to encrypt everything, and then that's going to be in tunnel mode. So to transport mode, tunnel mode, if you look at this little diagram, the difference is whether you have an encrypted original IP header or not. What step can you take to prevent unauthorized use of a remote access server?
Point to point. Okay.
Is the default for users to be able to dial in to be able to or not be able to dial in?
Be able to.
Actually, it's the other way around. The Windows, at least, the default is no. So what we want to do here, how we do this, is just don't give them permission to dial in, or only give the people that you want to be able to dial in permission to dial in. What's the function? What function does a smart jack serve?
I didn't write that down.
Demarcation point in place to move back.
Say it again, Tom.
Would be a demarcation point in place to do it back.
Yeah, loop back, and it terminates the T1 T1 digital lease line. Why would you use a T1 extender? Why would we need to extend the demarc? Oh, there it is right there, isn't it? Why would we need to do that?
Better access.
Better access, because our stuff's in the wrong place where they brought it in. It says if a customer premises equipment to CPE cannot be installed at the minimum point of entry, it may be necessary to extend the T1 lease line to another point in the premises. This can be achieved using an extender or line driver. What general steps could you take to troubleshoot a lease line exhibiting a high level of interface errors? By checking the error log. It says investigate the device to obtain the error statistics and perform diagnostic tests. Problems can sometimes be solved by resetting an interface or disconnecting and reconnecting the line. That's a Windows thing, right? Actually, that is true. And sometimes it's called bouncing the interface. And what they say is if you're doing it remotely, don't bounce the interface. Bouncing the interface is when you shut it down and bring it back up. If you're doing it remotely, it'll be happy to shut it down for you, but then you'll be disconnected and you won't be able to bring it back up. A VPN user is unable to access the company's website by name. The website functions as both an intranet and an extranet. You establish that a connection can be made by IP address. What's the likely cause? Is what? We can connect with the IP address, but not with the fully qualified domain name. DNS. The website functions, let's see, it says, you might suspect a split horizon DNS configuration. A VPN user should be using the internal DNS service to access the site as an intranet. Using the name that resolves for the extranet, external clients will fail. Check which DNS server the VPN interface is using. That one actually, yeah, when you have those split horizon things, it can get complex as to which DNS server you're using or which one you configure to use in any or other.
Intranet.
Yeah, intranet is the inside and extranet is the outside. So which address is it actually resolving? And if you're inside and it's resolving the outside address, then it ain't gonna work. Questions? I don't have any other talking to do tonight. I know you guys are tired of listening to me.
Same bad time, same bad channel tomorrow.
Same bad time, same bad channel. We're in the, okay, tomorrow, if you want to look at this stuff or have an idea of what we're going to do, tomorrow we're going to start Module 5, which is the last one. is security, and we'll do Unit 1 and Unit 2 and then Labs 16 and 17. The Unit 1's vulnerabilities and threats, and Unit 2 security appliances. And then on Thursday, authentication, incident response, change configuration. Then you will evaluate the course, and I guess we'll be done with it. Then you guys get practice time, right? I understand. Is that right?
I checked with that. They said that you have access to the labs for about 6 months.
Yeah.
For longer even.
Yeah. Anybody got anything else? Or you want to hang around for another 15 minutes, or you want to quit?
Well, it's been swell.
I'm gonna go to bed.
Have a good evening.
Yes, sir. Everybody have a good one.
Good night, everyone.
Good night.
Bye.